Hi everyone, today we want to look at the integral test. So we've looked at previous tests, we've looked at the test for divergence. We've kind of just assumed that if you can take the limit of a certain series and you can determine that it equals 0, then you have yourself a nice proof that your series converges. Although we did not really determine what it could converge to until in the last video when we talked about the geometric series and how we can find infinite sums of the geometric series. So that was nice to see. And it was also very helpful. The geometric series is something that we know quite a lot about. But now we would like to look at some other types of series. These types of series we might not be able to find the exact value that it converges to. We need to estimate it. That's what we're going to be looking at in these next couple of videos. But today we want to introduce something called the integral test. As you can imagine, it has to do with integrals. So we're actually going to be using some calculus to determine if a series converges or does not converge. So if we have a continuous positive and decreasing function on the interval between 1 and infinity, so that could be many things. So it could be something that comes down nicely like that, or it could be something that's really it's not very well behaved until we get to 1 and then it decreases like that. Stuff that is like that. It is positive, decreasing, and it's continuous on the interval between 1 and infinity. So if those are satisfied, we can correspond every a sub n value with an f sub n. So we can correspond our series with a function. So then if we take the integral of our function between 1 and infinity and it's convergent, so it doesn't equal infinity, then the series is convergent. And the same goes for the divergent side. So if our integral between 1 and infinity of f of x is divergent, then our series is also going to be divergent. So this is pretty easy. We know how to take improper integrals, and what we can do is we can correspond our a sub n into a function, and then we can integrate that function and determine whether it's convergent or divergent, and that corresponds to whether our series is convergent or divergent. Now again, this doesn't tell us anything about what it converges to or what it diverges to, although that would be infinity. It just tells us whether it converges or diverges, kind of like that limit test. Okay, so we want to throw this integral test at one example that we want to talk about, which is called the harmonic series. So the harmonic series is a very important series, and it is just the sum of 1 over the integers. So if I have the sum from n equals 1 to infinity of 1 over n, that is the harmonic series. So that's 1 over 1 plus 1/2 plus 1/3 plus 1/4, and so on and so forth. All right, so what is this going to look like? So we need to graph it, first of all, to make sure that it's positive, decreasing, and continuous. If I do f of x equals 1 over x, well, if I take f of x equals 1 over x, we've got that asymptote at x equals 0, but at x equals 1, we're looking pretty good. We're just going to be going down like that into an asymptote. So that is decreasing, positive, and continuous. Wonderful. So now we have satisfied the conditions for the integral test. So now we can use the integral test. So is the sum from n equals 1 to infinity of 1 over n convergent or divergent? Again, we're going to use the integral test. So a sub n is going to go to f of n, and thus we're going to integrate f of x, which is going to be 1 over x, because we've got 1 over n, we just swap the n for the x, we get 1 over x. So we get the integral between 1 and infinity of 1 over x dx. Okay, so now we got to pull out a limit. We got to do all this stuff to make sure that all the math heads aren't going to explode when we put an infinity in the integral sign. We want to put the limit there so that we can integrate to a number. So get the limit as t approaches infinity of the integral between 1 and t of 1 over x dx. 1 over x is a very easy function to integrate. We just get a natural log. We can directly apply the fundamental theorem of calculus, and then we get the limit as t approaches infinity of the natural log of t minus the natural log of 1. Well, the natural log of 1 is going to be 0. And the natural log of t, well, that's going to be the natural logarithm of infinity. If we take that limit, the natural logarithm function goes out like that, and it keeps going up. So that's going to be infinity. So we get infinity. So our integral does not converge, it diverges. So then the harmonic series diverges. So that's important. If we take the sum, so if we take the sum from n equals 1 to infinity of 1 over n, that is going to be equal to infinity. So that might be a little bit counterintuitive because, well, this function is decreasing all the time, but it turns out that we keep adding and adding and adding, we get to infinity. Okay, so now we want to expand this. We want to expand the harmonic series to look at all of the series where we have 1 over n to the something power. So the harmonic series is 1 over n to the first power, so that's a special case of the p-series. But the p-series is the sum from n equals 1 to infinity of 1 over n to the pth power. Okay, so what it turns out, actually, is that we converge when p is larger than 1, and we diverge when p is less than or equal to 1. So a famous case of this is when we sum all of the squares. So we get n equals 1 to infinity of 1 over n squared. And if we sum all of those, well, then we are going to get something like pi squared over 6, which is a very interesting topic. There are a lot of videos about that, but it does converge. It converges to pi squared over 6. And that's an example there. Why it converges to pi squared over 6 is for another video.